In the physical universe, there is a strict mathematical rule governing everything around us. No single event, no physical object, and absolutely no piece of information is ever truly deleted from reality. Think about tossing a dense, heavy book into a fire. As the paper turns black and crumbles, it feels like the words are being erased. Hard drive. You change its state from a rigid solid into a glowing pool of liquid metal. The data is hopelessly corrupted to any human engineer, but every magnetic bit and atomic ingredient is still exactly where you left it, just vibrating in a different arrangement. Or consider dropping a pristine diamond into the Mariana Trench. It is permanently lost to human retrieval, buried under thousands of tons of crushing water. But it hasn't vanished from the universe's overall ledger. The diamond exists. It simply changed its coordinates. Every form of destruction we see is actually just a reshuffling of matter. Because every physical interaction is theoretically reversible, the universe never forgets. The present state of every atom contains the necessary code to reconstruct its entire history. This is the M87 black hole. It represents a direct collision between our two most successful theories: general relativity, which says nothing can escape this void, and quantum mechanics, which insists that information can never be destroyed. For a long time, physicists treated black holes as eternal prisons. Whatever went in, stayed in forever. But in the 1970s, Stephen Hawking proved they actually have an escape valve. Hawking realized that the extreme quantum environment at the edge of the black hole causes it to leak. It emits a faint, completely random thermal mist out into space, a phenomenon we now call Hawking radiation. Because the black hole is constantly shedding this radiation, it is slowly losing mass. Over a timeline spanning billions of years, it shrinks. Eventually, it vanishes entirely. If a black hole disappears, we have to account for the specific data of everything it ever swallowed. If that data isn't in the radiation and the black hole is gone, then the conservation rule has been violated. To see the conflict, look at this thought experiment. We have two identical black holes. We feed the one on the left a dense encyclopedia. We feed the one on the right a simple pile of sand with the exact same mass. Both black holes begin to leak Hawking radiation, but Hawking's calculations showed this output mist is featureless. It is entirely random and statistically identical, regardless of whether it was fueled by a book or by sand. Eventually, the black holes vanish entirely. We are left with two identical clouds of thermal radiation. There is absolutely no physical difference between the two remaining fields of static noise. You cannot work backward from these identical ashes to see which black hole ate the book. Because there is no hidden inside left behind, the unique atomic signature of that encyclopedia has vanished from the universe. This is the black hole information paradox. It suggests that the universe possesses a mechanism that can actually delete history, leaving us with a present that has no mathematical link to its own past. The stakes go beyond simple book burning. If information can be truly lost, the law of causality is broken. It means the current state of the universe is no longer a reliable map of what happened a second ago or a billion years ago. Predictability itself fails. Theoretical physicists refuse to accept this breakdown. Scientists like Kip Thorne and Leonard Susskind have spent decades searching for hidden escape routes in the mathematics of gravity to ensure that the past remains fully traceable. That search has led to a leading theoretical rescue mission known as the holographic principle. This principle suggests a swallowed object's data isn't destroyed. Instead, it's encoded directly onto the black hole's two-dimensional surface. As it evaporates, this surface data is woven into the outgoing Hawking radiation, escaping back into the universe where it can be recovered. These holographic models offer mathematical hope that history is preserved. But until we can observe these subtle patterns in the radiation, we don't know if a dying black hole ultimately saves our past or takes it permanently.